So you can see.
Yes, sir. Yeah.
Okay. So we did these, and I asked you that you can do this, and I think you did these, right? Okay. So now we are going to move to again further reactions of esters. See, what we discussed was that carboxylic acid and carboxylic acid derivatives, they undergo nucleophilic acyl substitution reaction, right? Whatever the group is attached to the acyl group, it will undergo a substitution provided the incoming nucleophile is a stronger base than the leaving group, right? That was the key condition, right? That the incoming nucleophile must be a stronger base than the outgoing group. Now, let us consider the reactions of esters, right? Now, let us consider this first reaction. It is called a hydrolysis reaction because the breaking is the breaking of this thing is taken by water, right? Hydro means water, lysis means breaking. So you can see that this is getting broken, and there's nothing new again here. The OCH3 group will be replaced by OH group, and it will be an equilibrium reaction. Why it will be an equilibrium reaction? Because alcohol and water have similar pKs, right? Also, you can see that we have used H plus. That is because CH3O minus is not a very good leaving group. So what we do is a protonation occurs, and that helps it to convert into a better leaving group. Other reaction is a transesterification reaction, meaning we are converting it from one ester to another ester. For example, this is one ester and I have converted it to another ester, and this is my nucleophile, right? So the products are very easy, right? Products we can immediately write, right? And an aminolysis reaction, again, as we can see, that again the nucleophile has substituted this particular group, right? And the H plus is lost, as we talked about the thing, right? So these are the three reactions. There's one hydrolysis of an ester, which is going to give me a carboxylic acid as product, and you can see that it is an equilibrium reaction. Then we have a transesterification reaction. Again, you can see that it is an equilibrium reaction. Both hydrolysis reaction of an ester and transesterification reaction, we are using an acid catalyst, right? Please keep this in mind, right? And finally, when an ester reacts with an amine, we are going to get an amide, okay, right? And if you remember, we were using two equivalents for amine in the case of acyl chloride, and in this particular case we are just using one, right? So why is that? That is because when this particular group leaves, this RO minus is much more basic than amine. So this is the one which picks up the proton. So amine is not amine does not react with the acid. So amine remains intact and it can act as nucleophile. So we do not need to give two equivalents to it. Okay, that is the thing. And again, that is all. So what I want you to do is starting with methyl acetate. Okay, what neutral nucleophile you use to synthesize each of the following compounds? So you can do A, B, C, D, and you can send it to me. Okay.
Yeah, yes, sir.
Okay.
Yes, sir. Done.
Send it to me.
Yes, sir. Sent it.
Okay. Whenever I ask you to do, we will never draw phenyl or benzene ring where we have drawn a circle. We will always draw the bonds. Okay.
Okay. Yeah. Yes, sir.
Yeah, the circle makes the mind circle. Huh? Okay. We'll never understand this. And other thing which I want to tell you, I just told you that when we have to make the amides from the esters, we do not use two equivalents, right? Because RO minus is more basic, so it is the one which picks up the proton. So amine does not pick the proton, so amine does not get destroyed. Okay.
Oh, okay. Yeah. Yes, sir. This
Yeah.
is the other one.
So
Yeah.
notice that
SCl.
aminolysis of an ester requires only one equivalent
One.
of amine, unlike the aminolysis of an acylhalide, which requires two
Yeah.
equivalents.
Two
Okay,
equivalent. Yeah.
got it, got it. Okay, awesome, awesome. And explain why it is. Okay, you can try this as homework. You can think about it. Okay. So again, oh, now see. Now do problem 17. Okay. We'll do some problems in the class. Do problem 17, and then I want you to look at this problem 18. It is solved, but I want to. And then I want you to do problem 19. Okay.
So 17, 18, 19, right?
Yes, yes. 17, 18. I made up the playlist. Did you see?
Yes, sir. Yeah. I saw it.
Okay, okay. More things for you. Yeah.
So hereby uncatalyzed doesn't mean that it has to be a neutral nucleophile.
Yes, the uncatalyzed means what is going to happen? We are not going to use H plus.
Yeah. So it has to be neutral.
Yes, yes.
Yeah. Yes, sir, done.
Okay, send it.
Yeah. Yes, sir, sent.
Okay. Now, before the tetrahedral intermediate kicks out the CH3O minus, a proton is lost, right? When the nucleophile is neutral, right?
Yes, sir, yeah, but I didn't know like how the proton will go because
We just
there's
we just
nothing
make the
to.
proton go. Okay, H2O will pick it. Okay.
So it just leaves on its own.
Yeah. Okay. No, it will not leave on its own, but
Yeah,
H2O
we
will
leave
pick it.
some
Huh?
base. Yeah.
Okay. So yeah, because the tetrahedral, remember whether the nucleophile is negatively charged or a neutral nucleophile, from where it is expelled is the same, right?
Yeah.
So OH2 plus cannot be there. It must be OH and then it will go. Okay.
Yeah. Yes, I got it.
Got it right? Same thing with the other one. Okay. The proton must be lost.
Yeah.
And when the proton is lost, you see in the cases like this, I'm just showing this your carbon and this H and this H say CH3 and this plus proton always go like this, not like this. This is how you are taught in the schools,
Oh, okay. Yes, I'll go towards
right?
the
Towards
positive.
the
Yeah.
positive, right?
Yeah.
Yeah. Okay. Correct this and yeah. Then you go to 18 and then go to 19.
Yes, I went through 18 and 19.
Okay. Then do the 19.
So for 19, A part I'm getting phenyl acetate,
Yeah. Okay.
and B part I got methyl acetate.
Okay. Yeah. This looks correct. Okay. How are we deciding now?
So which is the weaker base?
Yes. Okay. So we compare the acidity. Okay. Right. Of the leaving
Yeah.
group. We can, right.
Yeah.
Right. So we are done. You can do this as a homework. Now, acid catalyzed ester hydrolysis and transesterification. We just talked about this thing, right? So here we have done the mechanism in the case for when everything was neutral. Now this is very important. whenever we have acidic solutions, all organic reactants, intermediates, and product in acidic solutions will be positively charged or at best neutral. Okay, negatively charged species are not formed in acidic solutions. Got it?
Yeah, got it.
And all organic reactants, intermediates, and product in basic solutions are either negatively charged or at best neutral. Positively charged species are not formed in basic solutions. Clear?
Yes, sir, clear.
So now see hydrolysis of an ester with a primary or secondary alkyl group. See, now the first step is protonation. Huh? And we know that the carbonyl oxygen is more basic because of the resonance, right? On the carboxyl oxygen, there will be a positive charge, right?
Yeah.
In the resonating structure, resonance will be like this, right? RCO minus and double bond OCH3 plus. So that is why the protonation is occurring in the carbonyl oxygen. That is the first thing I want you to notice. Now, what is going to happen? The mechanism is again very simple. See, so I just explained why, because that oxygen atom has greater electron density. So what is going to happen? First step is the protonation. Now, in the moment the protonation has occurred, what has happened? This carbon, the delta plus here has increased manifold, right? Because oxygen has acquired a positive charge. So it means it is going to pull the electrons even more from this carbon atom, right? So this carbon is more susceptible to the attack by the nucleophile, right? Because on this carbon, the delta plus has increased. We can see the oxygen is positively charged. Clear, right?
So it was positively charged. How does the delta plus increase?
Because it will start pulling more, right? Because it want to release its positive, right? Oxygen,
Oh, okay, okay, yeah, got it.
right?
Yeah, yeah, yeah.
Okay, so that is why. So now it will be reacting fast. Now see, after the first step, this attack has occurred, we get a tetrahedral intermediate, right?
Yeah.
Now, as usual, this tetrahedral intermediate will lose its proton. So proton is lost. Clear till here?
Yeah.
Now I know that I have to kick out OCH3. So now the protonation occurs on the OCH3. You can also ask why not on the OH? If protonation occur on the OH, we again get this. Huh? Okay.
Oh, okay, yeah.
Okay. So here we are protonating the OCH3. Okay. So protonation occur in at OCH3, and now this has become a much better leaving group, right? This has become a much better leaving group because now the leaving group is this CH3OH and its conjugate acid is CH3OH2 plus. So here pK is less than 0. So obviously this is a much better leaving group, right? Because it will be neutral, right? Clear?
Yes, sir, clear.
Okay. And once it has left, you see oxygen is pushing out, and now the positive charge has appeared on oxygen. It has H and the proton is lost, and we finally get this product. See, take a while just to go through.
Okay, yeah, yes, I got it.
Right?
Yeah.
And here. See. So this is the tetrahedral intermediate 1. This is the protonated tetra, and this is the third. Huh? Okay.
Yeah, yeah.
Got it?
Got it.
Now we come to this. Now, Lee-Scheitler principle in the equilibrium reaction, as soon as methanol is formed, I'm going to collect methanol. So as the methanol is going to decrease on this right-hand side, what is going to happen? The equilibrium will keep on shifting and I'll keep on isolating, right? until all of my ester is converted into carboxylic acid, right? Le Chatelet principle, right?
Yeah.
Okay. So see the practical application of Le Chatelet, right? So we are distilling off the alcohol as it is found. Meaning I'm heating it to 100 degrees Celsius, right? Water. So we know that the methanol has a boiling point slightly less than 100, so it will evaporate, right?
Yeah.
So as soon as it is decreased, what is going to happen? The equilibrium will keep on shifting to the right side, right? Le
Yeah.
Chatelet principle.
Yeah. Yes, I got it.
Clear?
Yeah, clear.
Okay. When it is not clear, please let me know. Okay. Okay. Yeah, you can do this as homework. You can try. Okay. How an acid increase the rate of hydrolysis? See, first of all, it is going to protonate this, so it is going to be more susceptible to addition of a nucleophile, right? If you compare these left and right, left will be more susceptible, right?
Yeah, because the oxygen will
Yeah, oxygen is protonated, right? It just want to, and it also increases the rate of collapse of the tetrahedral intermediate, right? By protonating. So see, if it is uncatalyzed, then this has to leave. If it is catalyzed, this has to leave. So this is much better, right? Because
Yeah.
the oxygen is protonated. Got it?
Yes, sir, got it.
See, such, see, small things, huh? Okay. So great, great, great. Okay, now 23 and 24.
Yes, sir, done.
Okay, send it.
Yeah, sent.
Okay. Now move to 24.
Yes, sir, 24 also done.
Okay, great. This is quite simple, huh? Okay, nice. Attack. Okay, this proton has been lost. Very good. Protonated. Okay, opened, and H plus is lost. Five carbons. Excellent. Excellent. See, now we are going to deal with hydrolysis of an ester with a tertiary alkyl group. Huh?
Yeah.
Okay. Now what is happening here? The first here till here it is okay. Huh? Okay. Right? The protonation has occurred in the first step. Huh? Yes.
Yeah.
Till, but now what is happening? Oh my God! Instead of whatever used to attack and everything, this group this is going like this, huh? Why? Why it is going like this? SN1. See, see now you can see that this is acting as a leaving group, huh? And SN1 mechanism is taking place, huh?
Oh, okay, yeah.
Why? Because it can generate a tertiary carbocation. Got it?
Yeah.
Hydrolysis has taken in a very nice fashion, huh? Here, clear?
Yes, sir, clear.
Yeah. And finally, H2O plus will attack here, and I'll also get this alcohol, huh? See? Okay.
Yeah.
Now just take a while to just look at it. Okay, clear?
Yes, sir, yeah, clear.
Trans-esterification, again, same thing, same mechanism will occur, just like, okay, H2O, OH. Clear? Yeah, right. By this time, you know that ROH and H2 are brothers, huh?
Yes, sir, yeah.
Okay. So do 25 and send it to me quickly. And little nuances here. So yeah.
Okay, yeah, sir, done.
Okay. Send it. Yeah, you can do these as. This I'll put it for homework.
Yes, sir, sent.
Okay. So now this is hydroxide ion promoted. It is not, we are not using the word catalyzed. Okay. This is very important. We are using the word promoted. Okay. So like an acid catalyst also is a namely for, so it's the same thing, but yeah, it is a promoted hydroxide ion promoted. Okay. So hydroxide ion is consumed. That is what we mean. So how it will increase the rate of the reaction? Okay. That is the first thing we have to see. And yeah. And the collapse of the tetrahedral intermediate, again, we are going to see that how it is going to affect. Okay. See, hydroxide ion is a better nucleophile than water. So when we are going to use hydroxide ion instead of H2O, see what is going to happen. In the first step, it is a better nucleophile as compared to H2O, right?
Yeah.
And when the collapse is going to happen, okay, after the collapse, what is going to happen? See, CH3O minus will pick up a proton from this product because this is a carboxylic acid, right? And this is a base. So Neha, see what has
Okay,
happened.
yeah.
After this acid-base reaction, this is no more in equilibrium, right? This is no more in equilibrium
Yeah.
because now it cannot go back, right?
Yeah, yes, sir.
Right? From it cannot go from a strong acid to from weak acid to strong acid, right?
Strong acid,
So this
yeah.
is the main thing, that hydroxide ion promoted hydrolysis of an ester is an irreversible reaction, right? See?
Yeah.
Okay, that is the main thing, and where it is, okay. Oh, it must be here. So, and because once the RCO minus is formed, this carboxylate and anion nucleophile will not attack, right? Negative repulsion, huh? Already,
Yeah,
O
yeah.
minus is already a negative, huh?
Yeah, yes, sir.
Okay. So that is the thing. So this is a reversible reaction and this is a irreversible reaction. Okay. Got it?
Yeah, yes, I got it.
Okay. Great. We're going to come to this in a moment. So again, you can see what has happened here. Hydroxide ion promotes only hydrolysis reactions. Okay. It cannot promote reactions of carboxylic acid derivatives with, I'll use this. Cannot with alcohols or amines, because one function of hydroxide ion is to provide a good nucleophile for the first step of the reaction. Okay. When the nucleophile is supposed to be alcohol or an amine, nucleophilic addition by hydroxide ion would form a different product from the one that would be formed from nucleophilic addition of an alcohol or amine, right? So I cannot simply add HO minus here, right? Clear? Okay.
Yes, sir, clear.
Okay. So yeah, and then hydroxide ion can be used to promote a hydrolysis reaction. I'll use the different color here. It can be used to promote a hydrolysis reaction because the same product is found whether the nucleophile that attached to the carbon is H2O or HO minus. Okay. Now, react again. I'll change the color. Reactions in okay. Reaction in which nucleophile is an alcohol can be promoted by the conjugated base of the alcohol. So now we can do it. So if I'm using CH3CH2OH, I can use CH3CH2O minus, because this again is a good nucleophile, right? As compared to ethanol. Ethoxide ion is a better nucleophile, right? Yes?
Yes, sir, yeah.
Okay. Great. So that is what they are telling you. This was one question which came when I applied for IIT in 2000. See, I want you to 28. What species other than an acid can be used to increase the rate of the trans-esterification reaction that converts methyl acetate to propyl acetate? Okay. Explain why the rate of aminolysis of an ester cannot be increased by H plus HO minus or RO minus. Okay. So this is homework. Huh? Okay. Now this is a very nice thing. Problem 29. Huh? Just read this and then 30th is solved. 29, I want you to do. Just come from the wall.
Yes, sir, I'm with 29.
Okay, send it. So O18 will come to the ethanol, huh?
Yeah.
Oh, okay, okay.
So in the A case, right?
Where have you sent? Okay, okay, here it is. You have drawn the products, and in the end, you have drawn what product would be your friend? If the alkyl CO bond is obtained. Yes, yes, yes. Okay. Now you understand how they are using isotopes to get the mechanism right. What has happened? Which bond is broken, right?
Yeah.
Okay. See how sophisticated, right? So this they asked in 2000 J 2000 at our time, which I did correctly. Okay. Now what is this? You can. This is a very nice question. Okay, solved one, please. I'll just write homework. Solved. This one, just go through it, huh? Okay. Now reactions of carboxylic acid. See, this is the relative reactivities toward nucleophilic acyl substitution. Carboxylic acid, then amide and carboxylate anions do not react. Got it? They are even less reactive as compared to amides, right? Which makes sense because they are already negatively charged, so the collision will not occur between two negatively charged species, right? They'll repel each other. Yes?
Oh, okay, yeah, sir, yeah, got it.
Okay. So that is why nucleophile is not coming here, right? Because it is already. Okay, now the thing is carboxylic acid and an alcohol undergoes a nucleophilic acyl substitution reaction. Okay. Now let us see what is going to happen here. See, this is fairly clear, huh? This is also called Fischer esterification because this dude was the first to use the acid catalyst. Huh? That an ester could be carboxylic acid in the presence of. So it is called Fischer esterification. This is clear.
Yes, sir, clear.
Carboxylic acid and an amine can undergo an acid-base reaction because this is an acid and this is a base. See, proton has been picked. So we get a salt. This H plus will be picked.
Okay, yeah, yes, I got it.
And now look at this temperature. If we heat it extreme to the extreme temperature, then we are going to get that amide product which we would normally expect. Got it?
Yeah.
Okay. So now this is one another question, you see, I reframed this question like this. Suppose this oxygen is 18 labeled, okay, this alcoholic oxygen. Then in the product, now I'm going to draw multiple answer options. So one option will be like this. I will draw the same thing, this bromine, but here now I will draw it like this, O18. Got it? So this is incorrect, right? Because this oxygen will attack because this has more electron density. We'll come to this. First, you do this. 31st. Okay.
Yeah.
methyl butyrate and octyl acetate. Interesting. So in one case we'll use methanol and one case we'll use octanol, right? In presence of H plus, right?
Yeah, sir.
Yeah. Butanoic acid and acetic acid. Very nice, very nice. After this, see the salt one. Okay. See this proposal mechanism. First, let me delete all this. You're done with 31 or not?
Yes, sir. Just finished.
Okay. See, just look at this. Initially, a cyclic bromonium ion will be formed, right? Not that we will add both bromine. We'll go stepwise, right?
Yeah.
So after cyclic bromonium, why the cyclic bromonium has been formed from the down phase? Why is this down? Because this group is on the upside, right? This group is blocking in the upside. So it will be much better for bromine to come from the downside, right?
Yeah.
It has come from the downside. That is the first thing I want to tell you. Now the nucleophile can be either Br minus or oxygen can also act as a nucleophile, and oxygen will be in a better position because it is intramolecular. Huh?
Yeah.
And which of these oxygens will be attacking this? This one. Why? Because it has greater electron density. Huh? This we could have also attacked this one, right? But this will not attack. Huh? This will attack.
Oh, okay. Yeah, yes, sir.
Okay. So now, see if in the exam one is isotopically labeled, this star one. Okay. Let us say that this was isotopically labeled. So obviously, the final product will be where this star will come here. Huh?
Oh, okay. Yeah, yes, I got it.
So in the other options, I could draw options like these, huh? Where bromine, O, this, and double bond, and I can put a star here, huh?
Yeah.
Which is an incorrect one, huh?
Yeah, yes, I got it.
Okay, clear?
Yeah.
Okay, very nice. See, this is a good question, huh? This is called halolactonization, huh? Because ultimately we have formed a cyclic ester, so it is called a lactone, huh? Cyclic ester is called lactone. Cyclic amide is called lactam, huh?
Yeah.
So halogen is also being added, so this is called halolactonization, huh? This reaction, okay? This is not important, huh? Knowing what it is called, okay?
Yeah.
But it's a very popular reaction, and after that the bromine is removed. Huh? There are methods where we can remove the bromine. So we'll get a cyclic ester. So very nice way to form a cyclic ester, huh?
Yeah, yes, sir.
Okay. So yeah, this was another. Now we move and You can read this. Dalmatians do not fool with Mother Nature. You can just go through. Amides were my favorite because there will be no reaction. Amide is the least reactive, right? I cannot make acyl chloride from amides. I cannot make esters from amide. I cannot make carboxylic acid from amide, right?
Yeah, because amide is
Because the incoming is weaker.
Yeah.
See, my favorite are the amides. Okay, so we are done with this. Now we have this 33 and 34. Okay, do this. I think this month will be done with this in for the first go, and then in the second go we'll pick up a bit more intricate problem, and we'll revise this. Okay, for the second revision, and then we'll pick up the physical chemistry also to do that also.
So in 34, won't all the compounds form amide?
Sorry, in the
In 34, so
yeah,
won't most of the compounds form amide because amide is stronger than
in the A,
amide?
are we going to get an amide in A?
Uh, oh no, we need two equivalent.
We will just get an acid base reaction. In B, we will get an amide, right?
Yeah, in B and C.
B will get C, we will CH3 O minus. In the C also there will be difficulty. What about D?
So why will it be difficult in C?
There are two competing nucleophiles.
So but won't the amide be stronger anyway?
What reaction are we expecting here first? You tell me.
Oh, okay. Yeah, so the OCS3 is stronger because it's
That
negatively
is there,
charged.
but can CH3NH2 and CH3O minus react? I don't think so, right?
Yeah.
Yeah. In E, we will get an amide. Huh?
Yeah, E will get.
F, are we going to get?
No, sir, I don't think so.
Yeah. In the F, we are going to get the hydrolysis, right?
Yeah.
Because we cannot promote aminolysis in the esters, right? By a hydroxide ion, right?
Yeah.
That was the message we got, right? Clear?
Yes, sir, clear.
So yeah. So in the case of yeah, we are going to get in the A, in the B, in the C. Yeah. So yes. In the first one, we'll get a simple, right? We just discussed what is going to happen here, right? In the first one, we are simply going to get the acid-base reaction.
Yeah.
Great. Okay. And what about this now? Acid catalyzed amide hydrolysis and alcoholysis. See, now we said that amides will not react with anything, but again in the presence of H plus, see what is happening? We are able to form esters and carboxylic acids. Okay, and this we will be able to do because the protonation will be there. See the mechanism. In the first step, this has occurred. Okay, in the first step, this oxygen has gotten protonated. Yes.
Yeah, yes, sir.
In the second step, this attack will occur. Till here it is fine. Whenever this attack occurs, this will tetrahedral intermediate will lose its proton. Clear?
Yeah, yes, sir.
After that, now the protonation will occur on the group we are trying to. Why? Because after the protonation, it has become a very good leaving group. Weaker base. Nitrogen has acquired a positive charge. Got it?
Yes, I got it.
See? And then the same thing. Okay. This goes, this kicks, and NH3 picks up a proton. Got it?
Yes, I got it.
So that is why in the presence of, we can catalyze it. Okay. With the presence of an acid. Okay. The same thing. Okay. Got it?
Yes, I got it.
So,
So it's same as ester only, right?
yeah. See. And same thing, we are able to make the ester also.
Yeah.
So that is only because we are able to convert it into a metal. Why it is needed? Catalyst is required. Obviously, a catalyst is needed because on the left side we can see nitrogen has acquired positive charge, so it is very eager to get out. Where on the right hand side, NH2 is not at all eager, so it will kick out the OH only. This is a stronger base. This
Yeah,
won't
yes,
go
a
out.
stronger
Got
base.
it?
Yeah, got it.
Now this is penicillin. Yeah, they have shown yeah, they must have shown. This was penicillin G. This is the most active part is the beta lactam ring. The four-membered ring. I was talking about it yesterday, right?
Oh, okay, yeah, yes, sir.
The four-membered ring. I think it did it in 1957. Okay. The discovery was there, but J.C. Sheehan did it, right? J.C. Sheehan is not mentioned here, I think. It's so far. Yeah. Yeah, he's not mentioned. It's okay. No problem. He's done his work. See, this four-membered beta lactam ring is the reason why it is very biologically active. I don't want to get into this because for the time being. Because right, this four-membered ring will be sp2 hybridized, so 120-degree will be very difficult to achieve. So it is immediately it wants to open up this amide. This is an actually cyclic amide. R C double bond O N. Got it?
Okay, yeah, yes, I got it.
Okay. So that is how it is. Yeah, we'll come back to this. We don't have to do much of this. Okay. Now, right, the mechanism for an acid catalyst again. And then you can do the 36th. Just write BSc. No need to draw the structures. You can tell me only. No need to send also after you're done. What is going on in school, Neha? And what about the notes which I gave you? Are they helping you?
Yes, sir. Yeah.
You are doing, you are using them or not? With
Yes, sir. Physics I'm using, but math again the chapter got over.
now, what is going on in maths?
Definite integration, but sir, I think that's also almost over. I'm not sure what the next chapter
Definite
is.
also, did I send you? Did I send? No.
Sir, I'll just check. Oh, okay, yes, sir. Yeah, definitely, sir. I thought it wasn't there. Yes, sir. I'll go through it. Yes, sir. And I got B, C, A.
Okay, B, yes, it will be the best leaving group. Then C, then A, right? Weak
Yeah.
base, huh? Right? Weaker bases are better leaving group, so we'll see which acid is the strongest, like that, with right? Yes.
Yeah.
For example, here in the B, I am discussing what is the group that will leave? This will leave, and immediately I will draw its conjugate acid by adding H2. So I'll compare the acidities for these, right?
Yeah.
So NO2 is pulling out, so it is helping it, right?
Yeah, yes, sir. Making it weaker.
Yeah, this will be the weakest base, right? Because NO2 is pulling an electron from here. Then these electrons are in resonance here. And this is the strongest base because the nitrogen has all its electron fully available. Huh? This is the
Yeah.
strongest base. Huh? So weakest acid basically. So conjugate will be the strongest base. Got it? See, for the leaving groups, what I have done is after the leaving group, I have added H plus to everyone. And now I'm comparing which one of these is most acidic. So most acidic because we use pK values, right? So you can see it in multiple ways. So weaker base will not share their electrons well. Here it will not share well because NO2 will be pulling, and also it is in resonance. Here it is just in resonance. So right, and in this particular case there is no resonance, so it will be fully attached. So it will be most difficult to pull out, right?
Yeah.
Okay, I'll just let it go. Now amides can also be hydrolyzed when heated under strongly basic conditions. So see, I just okay. So here we have reached. Okay. Again, both are irreversible reaction because then again NH4 plus is here, so it cannot attack. This is the point which I wanted to tell you. Okay. And here also it will be, see the first step, HO minus has attacked. This is fairly clear in the first step, right? This first step.
Oh, okay. Yeah, yes, sir.
Now what will happen after this attack? You see, it is hydroxide ion promoted. So one more HO minus is getting used and it is removing, because the medium is basic, right? See, it has removed this proton also. Now imagine this species. Now both O minus are kicking it out. So that is why it is going, huh? Else NH2 minus does not go, right?
Yeah.
So because both of the oxygen are working, got it?
Yes, sir. Got it.
Both the oxygens are negative. So that is why it is called hydroxide ion promoted. Okay. Now this is Gabriel thalamide synthesis. Okay. So this is quite important. See, we are able to convert an alkyl halide into primary amine. Now, normally in the normal fashion, we cannot convert because multiple alkylations occur. Exhaustive methylation, if you remember. If you do not, you can go back. Okay, in the alkyl halide chapter. Here, what happens is like this. If I simply treat CH3Br with say NH3. So first it will attack, then till here I'll get CH3 NH3 plus. So
Yeah.
in the presence of K2Cr, K2CO3, this is a mild base. I'll get CH3 NH2. Now this will again attack CH3Br, and this keeps on happening until we get this salt, quaternary ammonium salt plus and Br minus. Okay, you can revisit it. So it is not very easy to form. So now they have presented a very roundabout way, and I really like this. See what is going to happen here. See, they are using phthalimide. So this is the structure of the phthalimide. Got it?
Okay, yes, I got it.
This is a phthalimide. And it's a cyclic amide, RCONH, and from it, this side also RCONH.
Yeah.
Now, the first step is fairly clear. This base has picked up this most acidic proton. Why? Because after the proton losing, this N minus, this is immediately resonance stabilized, right? Because the N negative can be delocalized to both the cases. So that is why it is good acid, right? Because I can draw like this also, O minus double bond, and on this side also. See?
Yeah, O minus double.
Got it? Clear?
Yes, sir.
Clear?
Yes, sir. Clear.
Okay. And after that, this is a nucleophile, right? And it is a nucleophile, and obviously what will happen? It will attack the RPR. So SN2 reaction has occurred. Now, this is called an N-substituted imide. What it is called is not important. Now, the important thing is, when I hydrolyze it, see how I'll form the product. I know that when I hydrolyze the amide, I get a carboxylic acid. So, you see, I add OH to these. See? C double bond OH. Huh?
Oh, okay, yes, sir. Got it. Yeah.
In the single one, we just get this, right? H plus H2O, we get RCOH, right?
Yeah.
So from two ends, we'll get RCOH, right?
Yes, sir. Yeah, got it.
Okay. And obviously, since the medium is acidic, when the amine has come out, it will be immediately protonated.
Yeah,
This will
yes,
come
sir.
out,
Got
right?
it. Yeah.
Okay. So it will not stop at RNH2 because the medium is acidic. Immediately H plus will be added and I'll get this.
Yeah.
So in order to get a free amine, I have to treat it with a base. The moment I treat it with a base, I get a primary amine. And also phthalic acid will also react with base and it will become a carboxylate anion. Got it?
Got it. Yeah.
So in the multiple options, they'll add like COH plus RNH2, CO minus plus RNH3 plus. Got it?
Yes, sir. Got it.
Okay. Nice. 38 is what you have to do. See, so whatever amine I have to make, I have to use that long carbon alkyl halide, right? So
Yes,
for
sir.
pentyl amine, I'll use pentyl bromide and all that.
Pentyl bromide. Yeah, yes, sir. Finish now.
Also, this is the only thing I want to. I cannot prepare this amine. For example, if somebody asks me, can we prepare this amine? This amine I cannot prepare because this has to come from this alkyl halide, right?
Yeah, yes, sir. So,
And
yeah,
here SN2 will not go, right?
yeah,
So we cannot prepare aryl and vinyl amines, huh?
yes, sir. Yeah,
You're getting it now, right?
yes, sir. Got it.
Okay.
Yes, sir. Done with 38.
Okay, you can send and you can also look at the problem 39. Huh? Okay, look at it at home in the homework. When you go home. Nitriles are these compounds. Naming nitriles, ethane nitrile. All carbons are counted. You can go through this. And there's only one reaction of nitrile. I used to love nitriles in my time. Just hydrolyze them and get an acid. Huh? Okay. See, so nicely.
Yeah, yes,
So
sir.
how it is happening? First, that this is protonation is taking place. See, in the first step, what is happening? There's a protonation which has taken place. See, okay. Obviously, this will happen, right? And now this carbon has become more susceptible to nucleophilic attack because there is a positive charge on the nitrogen. Got it?
Yeah.
This H2O will come very fast on this carbon, huh? Because the nitrogen got protonated. See, once the nitrogen is protonated, this has started pulling electrons even at a faster rate, right?
Yeah, so it becomes also susceptible for it.
Right, because it is more positive. Got it? It was
Yes,
already
got it.
electronegative. It was already creating this delta positive. But once it has become protonated, it will even, the inductive effect will be even more pronounced, right?
Yeah.
Then H2 has attacked, same thing has started. H plus is lost. And again, you can go through this mechanism. Okay. I was never interested much in this mechanism, but it's a very nice and simple mechanism. There's nothing that you won't be able to do here. Okay. The same thing will keep on happening. Okay. Once we have gotten an amide till here, see, we have gotten an amide and then we know the hydrolysis of an amide in the presence of acid will give me the corresponding carboxylic acid. Got it?
Yes, sir. Yeah, got it.
Okay. So other steps are you can just go in and see. Main thing is that RC, and it's a very nice method, you know, where I can increase the carbon chain length by 1 and then immediately. Got it? Clear? Okay. So we are going to leave till here and then we are going to proceed in the next lecture. Okay?
Yes, sir. Yeah.
Okay, Naya. Take care. I'll upload this. Huh?
Yeah.
Okay. Bye.
Thank you, sir.
Bye.